to the ceiling. Now the thread is coming out from this side horizontally. Okay, and from this side the thread is dangling vertically, let's say. Now some external agent is pulling this end of the thread with a velocity of, let's say this point is E, it has a downward velocity of 1 meter per second. And this end of the thread is being pulled horizontally. This end is, let's say, B. So this end is being pulled with a horizontal speed of 2 meters per second. So we have to find the speed of this block. Okay. So Devesh, this is the question you have sent, right? So whether it is this question or any other problem like this now with constraint relation, yeah, Ganesh, very good. We will use the easiest method to use here is the virtual power method. That if this is a massless thread, so it will have uniform tension everywhere. Okay, yes, 1.5 is correct. Okay, so the theorem we will use here, more importantly, is that the net power delivered by tension in the system should be equal to 0. Okay, so tension, the power delivered by tension at the point B plus the power delivered by tension on the block plus the power delivered by tension at the point A, the sum of these should be 0. So you can see that at this point, tension is acting opposite to velocity. So it is minus TVB. But at this point, 2T is acting on the block and its velocity is in the same direction. So plus 2TV. Okay, and then again at the point A, it is minus T into VA. This should be 0. So as you can see from here, you are getting VS, VA plus VB. So this is a very direct application of this concept. Okay. So it should become 1.5 meters per second in this case. But what I'm trying to illustrate is this is a universal method we can use no matter how complicated the problem is. Okay. So let me demonstrate this with another example, which I believe will be useful and important for you people also. So first of all, Devesh, hope this question is clear, right? Okay, good. Okay. The next example we'll discuss is a little bit more involved than this. Okay. So we will see that there is application of various concepts of mechanics we'll bring into play here. Let's say I have this kind of a system. Okay. Another pulley here. And finally, the thread going round like this. This is attached to another block B. This is attached to a block E. So now see all the parameters that are given to us. This height H, this angle theta. Okay. So mass of A is equal to mass of B. This height is, let's say, 50 meters. Okay. Now at T equal to 0, A and B, the two blocks are released from rest. With theta equal to 37 degrees. Okay. This is a smooth surface, no friction involved. Okay. So first thing, find VA and VB at an instant later when theta is equal to 53 degrees. Theta will increase with time, as you can see. Assuming that B does not hit the floor. Assume B has not hit the floor yet. Okay. And next part is going to be a little bit more tricky for this. We have to find the instantaneous accelerations at that instant when theta is 53 degrees. Find the acceleration of A and acceleration of B at the instant when, again, theta is equal to 53 degrees. Okay, so just try this out. So the general statement of the virtual power or the virtual work theorem. Okay. In a system with inextensible threads, inextensible and light threads, okay, the net power or net work done by tension should be equal to 0. So people, you're working on it, I hope. Okay. Can anybody tell me what is the displacement of B when theta goes from 37 to 53? To solve the first part, now I need to find delta y, that is the vertical displacement of B. Okay. As theta changes from 37 degrees to 53 degrees. So can you tell me how much that will be? Yes, Samyak, I will be discussing that question. Within the next half an hour, I plan to discuss all these things. Vertical displacement you're getting as 15 by 4. No, that is not correct. I think it should be 125 by 12 in meters. Okay, so initially it's like this, let's say. Okay, so this angle is 37 degrees. Okay, so let's say this thread length is L1. So L1 is how much? It is h upon sine 37. Na? So it is 5 by 3 h. And h is given to us as 50 meters. Yes, is that now? Good. Okay. So यहाँ पे U0 है, A का भी और B का भी U0 है. Now after some time, E reaches here, let's say. Okay. So that time this angle has changed to 53 degrees. So by now A has some speed VA and B has come down. Okay. So if B has come down by displacement Y, let's say over here, okay, and this length has become L2. So L2 you can see has become h by sine 53 or 5 by 4h. Then 2y, the extra thread length here, should be equal to L1 minus L2, the thread length released from there. Okay? So y should become 1 by 2 of 5h by 3 minus 5h by 4. So I believe this calculation will give you the value of y as 125 by 12 meters. And you can approximate that whatever. Okay. So now the next thing is you have to find the constraint relation between VA and VB before you apply work energy theorem. Okay. So that is where your virtual power thing will again come in. If the tension in this thread at this instant is T, so the instantaneous power delivered by tension on A plus B should be 0. So on the block A, tension is acting at an angle of 53 degrees with respect to the direction of its velocity. Okay. And on the block B, there's a net tension of 2T acting upwards and its velocity is VB downwards. So power delivered on A by tension is TVA cos 53 and power delivered by tension on the block B, that is minus 2 VB, minus 2 TVB. So this will tell us that TVA cos 53, which is 3 by 5 minus 2 TVB should be 0. At the instant when theta is equal to 53 degrees. So we will get this relation that VB is equal to 3 by 10 V. So this is one equation that we have. This is the constraint relation that we are getting between VA and VB. And then we apply work energy theorem. So the two masses are the same. So change in kinetic energy of A plus B plus change in gravitational potential energy of B should be 0. So 2 times, sorry, not 2 times, half mVA square plus half mVB square. Minus mgy should be 0. So we can write this like this, that VA square into 1 plus 9 by 100 should be equal to 2g into y, and y is 125 by 12. So this should give me VA. So VA will come out to be that will be approximately 'Yes, Ganesh, your answer is correct. Very good. Okay, and VB will be 0.3 times this. So approximately 4.15 meters per second or 4.2 or whatever. Okay. Now the more tricky thing here is to find out the accelerations. So I'll come to that. So acceleration के लिए for the constraint relation, we'll have to take theta as an instantaneous quantity. When you're writing the constraint relation between VA and VB, you'll have to take theta as a instantaneous quantity. So that's the tricky thing here. Okay. So if this angle is theta, whatever instant of time, and this block is having a velocity VA, and this block is having a velocity VB, and therefore this is having an acceleration AB, and this is having an acceleration like this. Then we have the constraint relation that VA cos theta is equal to 2 VB. This is coming from virtual power. Okay, so when we differentiate this, we have the time rate of change of this quantity is equal to the time rate of change of this quantity. So when we differentiate here, remember that theta is an instantaneous quantity. It's not constant. Okay, so this will be acceleration of A into cos theta plus VA into minus sine theta into d theta by dt. This quantity. That should be equal to 2 times EV. So a constraint relation is like this, that acceleration of A into cos theta minus BA sine theta into d theta by dt is equal to 2 times EV. So we have to solve this. Okay, at the instant when, so when theta is equal to 53 degrees, at that instant, you already saw VA was at approximately 13.8 meters per second. So you got that, but we need to find out what is d theta by dt. Okay, so for that, there's a very simple situation that you can see that if this is the instantaneous position of the block A, this is a fixed height, and this suppose is x. So you can see that x is equal to h cot theta, right? So dx by dt, which is actually minus VA, because this is moving in this direction, is equal to rate of change of h cot theta. So this is my constraint relation, that minus VA is equal to h into differentiation of cot theta, which is minus cosec square theta into d theta by dt. So this will tell me that d theta by dt's instantaneous value is equal to VA's instantaneous value divided by h cosec square theta. So I can just write that as into h sin square theta. So this is an additional geometrical constraint. Okay. So this will have to be plugged in here. So we'll have to find out this value. Okay. So d theta by dt will become VA upon 50 meters into sine square 53 degrees. Okay. So we'll have to plug all this in over here. So acceleration of A into cos 53 minus, now this will become VA square, and there's a sine theta into a sine square theta, so it will become sine cube 53 degrees divided by h. Okay, this term will become like this: VA sine theta into VA by h sine square theta, so it will become like this. That is equal to 2 times AB. So this is our constraint relation. Okay, when theta is equal to 53 degrees and VA at that moment is equal to 13.8 meters per second, or actually we know it in square terms also, so we'll just use that value, and h is of course 50 meters. So a constraint relation is that much more complicated in a situation like this. Okay, so to be very careful when you are working on the constraint relation between the accelerations. Most of the time the question will ask you the constraint relation between the acceleration at the initial moment when the motion has just started. So at that instant VA is 0, so that middle term does not come. So it just becomes acceleration of A into cos 37 is equal to 2 times the acceleration of B. But that is at the initial instant, not at this instant when they're well into their motion. Okay, so let's plug in the values. So here we saw VA square was how much? VA square was this quantity now. So we'll just leave it as 13.8 only, doesn't matter. Okay, so that will give us this constraint relation, that this is uh, 3 by 5 acceleration of A minus 13.8 whole square by 50 into 4 by 5 ka whole cube. That should be equal to 2 times AB. So this is my equation 1. Okay, I'm not going to solve all the equations now because it's going to take time. So this is equation 1, then the free body diagram of block A. So on that, tension is acting like this at an angle theta, and there is no other horizontal force, other forces are vertical. So T into cos 53 degrees is m into acceleration of A. That's my second equation. Okay, and block B, of course, very simple. 2t mg acceleration of B. So mg minus 2t is equal to m into acceleration of B. So I have three equations and three variables. Okay, so acceleration of A, acceleration of B, and the instantaneous tension, the three unknowns. All three are instantaneous quantities here. So they will be solved by using these equations. Okay. Okay, so Devesh, I will come back to your question also. The second one that you sent, it's related to another question I'm going to do, which is also rotational mechanics application. Ganesh, I will come to your question also. Okay, but let's go through this particular question first. It's a very interesting question actually. So what is happening in this question is that we have like a rod, okay, which is attached by a thread, and this whole system is on a smooth horizontal surface, and the thread is fixed at this point P. Okay, so this is a thread fixed at the point P, and this is a thin uniform rod of length L and mass M. Okay, and the thread has a length capital D. Okay, now this whole system is on a smooth horizontal plane. Okay, so the whole system is initially at rest on a smooth horizontal surface. So the XY plane is the horizontal plane. Okay, that smooth horizontal surface with the thread taut. Okay, so the rod is at rest, that I've already mentioned, but with the thread just about taut. Okay, such that this angle, I think, was given to us as, just check the question once. This is a question that Samik has sent. Yeah, this angle is theta. Okay, so actually there is, in the original question, there is some kind of a wall over here where the thread is attached to this point. So this is like a vertical wall where the thread is attached at the point P. Okay. So the length of the thread is D, whereas the length of the rod is L. Now there is a particle of the same mass as the rod, which is moving in a direction perpendicular to the length of the rod at a speed v naught, and comes and impacts this end point. Okay, so the particle, same mass as the rod, okay, makes an impact at the end point of the rod and sticks to it. Okay, it sticks to that point on the rod. So the first thing we have to do, and theta is also given to us in the question. Okay, the system is initially at rest with the rod aligned to the x-axis, blah blah blah, negative axis. The bullet, so I've taken it as a particle, hits the rod at the right end with velocity and gets lodged in it. The impact is nearly instantaneous. What is it? So this theta is also given to us. It is cos inverse of 1 by 3. So given theta is cos inverse of 1 by 3, we have to find, first of all, what is the tension in the string immediately after the impact. Okay. that I've shown earlier. And we'll also find the angular velocity of the rod plus particle system about its center of mass just after impact. Okay, and then the second part, what we'll do is we'll calculate the tension in the thread just after impact, at the moment just after impact. So those who are seeing this question for the first time, now I just want you to just give it a moment and think of what are the principles we can apply over here. Then I'll come to it. Okay. What is the tension in the thread just after impact? Okay. Just give a moment of thought and see what principles we can apply, what all things we can conserve, what all things we can't conserve, are there any constraint relations, etc., that we can use. Okay. Okay, people. So let's understand what are the conservation principles we can apply. No, it is not that, because see, it is you cannot consider the thread plus rod as a rigid body, no? But the rod is independent of the thread. The thread is just applying a constraint that this point on the rod, let's say this point is the end A of the rod, that end A of the rod will do circular motion about the point P. That is about the only constraint. Baki, there is no other constraint like that that's in pure rotation about the point P. ऐसा नहीं है, okay? But also, if you consider the impulse acting during collision, okay, then you will get what thing we can conserve. Okay, so first let us look at the moment of collision. Don't worry about what's happening after the impact. So at the time when this collision is happening, this tiny particle coming here is making an impingement on this. तो ये इस पे जो है ना ऐसा एक collision impulse, it impacts it with a collision impulse like this. But then this experiences equal and opposite impulse. So on the system, these two are cancelling each other. They are internal. So they are the collision impulse. But the thread will jerk. The rod will tend to have a strong spin in this direction. So this point tends to go downwards like this. So immediately the thread will react by applying an impulse. There will be a sharp impulse acting through the thread, which will act along the direction of the thread. So this J is an external impulse on the system. And this is acting at an angle theta. Okay. And then we look at the system just a moment after the impact is over. So we'll understand that as a result of this external impulse, what has happened, the center of mass will gain a velocity exactly along the direction of the impulse. Now, because this particle is now stuck, it's part of it. Okay. So this system, its center of mass is here somewhere. We'll just figure out the direction in a moment. So the center of mass would have gained a velocity, a linear momentum, which is in the direction of the external impulse. This will be the direction of the VCM. Okay, so you can even divide that into X and Y components, and you can see that if I've taken this as my X and Y axis, the VCM will be along a unit vector minus sine theta I cap plus cos theta j cap in my unit vector system. Okay? And about the center of mass, the system would also get an angular velocity omega like this. Okay, but at the same time, the interesting thing is that this impulse is acting through this point. Okay, so we can conserve angular momentum about this point, or you can even conserve it about the point P. It doesn't matter, anywhere on the line of action. So we can conserve it. So if you looked at the system at the moment just before impact, also, just for your reference. So at the moment just before impact, my system was like this. So the only thing I can just about conserve is the angular momentum about the point A or any point on the line PA for the whole system. That is the particle plus the rod as a system. So just before impact, this had a velocity V0 like this and the rod was at rest. So we can conserve angular momentum for the system. Sorry, angular momentum, I can take about point P also, but any point actually lying on the, okay, about any point on AP, that line AP for the system, that is the rod plus particle, that is conserved. Okay. So let us apply conservation of angular momentum about the point A for the system. So this will tell us that just before impact it was mv0 L anti-clockwise. So this should become RCM cross total mass is 2m VCM plus ICM omega. Okay. So this should become I take the mod of this, it becomes this. So actually this term will also be anti-clockwise, this term will also be anti-clockwise, so it's fine. Okay, so अभी देखो VCM को भी ना मैं break कर दूंगा. I'll break it into Vy and Vx. Okay, and I can see that from the point A, the center of mass will be at a distance of 3L by 4 because they were equal masses. So this term will actually become 2m into Vy into 3L by 4. Correct. Okay. Now actually we'll see a very interesting thing. This omega will come out to be negative. The one that I've drawn, it will come out to be negative. But anyway, that doesn't matter just at the moment. Okay. So I'm assuming that it's clockwise. Okay. So this will be, this R cross MB term will be what? It will be anti-clockwise because V is like this. Okay. And in my diagram, I've taken this to be clockwise. So this will be, now ICM will be moment of inertia of the rod, that is ml square by 12 plus m into L by 4 whole square, plus moment of inertia of the particle, which is this. So ml square 1 by 12 plus 1 by 16 plus 1 by 16. So this, when you calculate, will come out to be 5 by 24, I believe. And just check my calculation once. Okay. So this should be, but this will now come with a minus sign according to my assumption, because I have assumed that this is uh, clockwise. Okay. So minus 5 by 12 ml square omega, because I have assumed that this is clockwise, whereas this is anti-clockwise, and this was also anti-clockwise. Okay. So let's just cancel out some terms. So we will get V naught is equal to 3 by 2 Vy. Now remember what is Vy. From here Vy is VCM upon cos theta. So okay, minus 5 by 12 omega L. This kind of term I will get. 5 by 24, is it? Okay, okay. Yeah, I think I've only written it 5 by 24 above. Okay, so this is my first equation. Yeah, so Modi, why it will be that you can see in the impulse picture. See what is the net external impulse. It's along this direction. Na? So the net external impulse will be equal to the change in linear momentum of the system. Oh, but wait. Change in linear momentum. No, this is not correct. Omega about center of mass hoga na beta, because see, it's a independent rigid body, na. So it will go into that combination of, yes. So wait, that's correct, Somadev. So this will be change in linear momentum. Wait, we will have to change this. Okay, just a moment. We'll have to change these equations. So the VCM will not be like this. Yes, Somadev, your point is correct. Okay, so we will apply this now. I mean, our equations were correct, but the values, we'll have to be a little extra careful. Okay. So let us just take general terms Vx and Vy. Okay. So let's assume that immediately after impact, yeah, very good. Thanks for pointing that out, Somadev. It was bad mistake. Just a moment, guys. Yeah, so what is happening here now, as Somadeep has very correctly pointed out, that the system does have this thing now, it does have initial momentum. So this equation will have to be applied. So our J external is like this. It is some J into sine theta, or rather minus sine theta I cap plus cos theta j cap. Okay. Uh, this will have to be equal to the change in momentum. So now for the change in momentum, now we will assume that the center of mass has some y component of velocity, let's say like this, some x component of velocity like this. And see Ganesh, what is happening now? आपके center of mass के about ऐसा impulse लग रहा है. So that will create angular momentum. Nice. The simple thing is that the net external impulse is equal to change in linear momentum. So that is m into delta v of center of mass. Okay. Total mass, that is. In this case, it's 2m, of course. And the angular, this thing, impulse, that is tau dt integrated about com. This is equal to change in angular momentum about center of mass. This is what happens for a rigid body which has no fixed axis. This is an unhinged or free rigid body. Okay. So of course the tension has a particular constraint here, but it's not giving it a fixed axis of rotation. Na? So we have to apply this equation. This is clear, na Ganesh? Okay. So about this, there is going to be an omega like this. Okay. So this is going to be equal to the change in this. So this side we can write it equal to, I'm just writing it here, m into minus vx I cap plus vy j cap. Sorry, 2m, because that's the total mass minus the initial momentum, which was mv naught j cap. Okay, so from this what we'll understand is that this unit vector, if you see on both sides, it's like this: j into minus sine theta I cap plus cos theta j cap. On the left hand side, what is the x component? It is minus 2m vx. And what is the y component? It is plus m into 2vy minus v naught. Yeah, yeah, na? So when we compare the two unit vectors, this one's unit vector must be the same as this one's unit vector. So this term divided by this term should be this by this. Okay. So 2vy minus v naught divided by vx, sorry, divided by 2vx should be equal to cos theta divided by sin theta. Okay. Or we should have this constraint relation now. So I'm rubbing this. This was from the previous section. So our constraint is a little bit more complicated between Vx, Vy, and V0. Our constraint relation is going to be like this: that 2Vx is equal to tan theta into 2Vy minus V0. This is going to be our first constraint relation. Okay, where we know that cos theta is 1 by 3. So tan theta will become how much? It will become 2 root 2 by 1. Okay, so tan theta is 2 root 2. Get this picture. So this will become this equation. So guys, hope this is clear. Okay. Now the other thing is what? That the point A over here is doing a circular motion about the point P. So the instantaneous velocity of the point A must be tangential to the line PA, or its approach velocity to the point A must be 0. Okay, so the second thing we will use is a geometrical constraint. Now see, my center of mass is having some Vy and Vx, and about the center of mass there's omega like this. So this point A, its net velocity will become this vector sum of Vy, Vx, and this thing 3L by 4 omega. So that's where I'll actually understand that omega is opposite to what we have taken it to be. Okay. So basically the velocity of the point A in the ground frame should be equal to velocity of point A with respect to center of mass plus the velocity of center of mass. So that is nothing but omega cross r of A with respect to center of mass plus BCM. So when you look at this term according to my omega, this term should be 3L by 4 omega j cap, okay, and BCM is minus Vxi cap plus Vyj cap. So that is how I should get the velocity of the point A to be minus Vxi cap plus Vy plus 3 by 4 omega L j cap. I should get this as the velocity of the point A. Now the velocity of the point A as a vector should be in this direction. If this is the direction of the thread, okay, so this net velocity should be in this direction actually. It should be along this axis. So the velocity of the point A, let's say, should be either like this or like this. Okay. So here, when we finally work it out, you will see it will come out to be in this direction because my omega will be negative actually. So this velocity should be perpendicular to the line PA because A is in circular motion about the point P. So the distance d from the point P should remain constant. Okay, so that also means that approach velocity of A towards P should be 0. So that will give me another constraint relation. Okay, so let's apply this thing now. So if approach velocity towards the point P should be 0, that's how you'll see that you have to make omega opposite. Omega will have to be a negative quantity compared to what we have seen. Okay, and that also you'll understand why that's happening because the system had so much angular momentum in this direction before. No? It had so much angular momentum like this that this will not dominate. Eventually omega will be like this only. Omega will be anti-clockwise and not clockwise. But anyway, let's demonstrate this. So this angle is theta here, so this angle will become theta. So we will have Vx sine theta plus Vy plus 3 omega L by 4 whole thing into cos theta should be 0. So we will have this relation that Vx sine theta plus Vy cos theta should be equal to minus 3 by 4 omega L cos theta, or that omega should be minus of what we have taken it to be, or let's just write it as omega L because dimensionally it will make better sense for us. So this will be minus of 4 by 3 of Vx tan theta plus V1, this kind of term. So this is going to be our second relation. Okay. So now remember our unknowns are Vx, Vy and omega. So we need one more equation. We have got two equations so far. Okay. As you can see, one equation we got from angular momentum conservation about the point P or about the point A, whatever. Oh, we have not written that equation yet. Okay. So anyway, so this is the first equation that we have got from this thing, from the impulse concept. Okay. And yeah, okay. And we still have the angular momentum conservation equation to write. Okay. So that is the equation we had written earlier. That was a correct equation. No problem with that. Okay. Yeah, I'll just verify for you, Samadhi. Okay. So the external impulse is acting through the point A. Okay. So angular momentum about A for the system should be conserved. Okay, because J external was through the point A. Okay. So as we had seen earlier, that equation was okay. There's no problem with that. Okay. And after impact, you have Vy, Vx. And I have taken omega like this, but omega will actually be a negative quantity. So we'll come back to that. Okay. So mv0 L, which you can see about A is anti-clockwise, should be equal to 2m Vy into 3L by 4. Okay. Is also anti-clockwise, but minus ICM, where this is the center of mass. Okay. Omega, because I have taken omega to be clockwise. Okay. So this is going to be my third equation. So in this, of course, I will substitute ICM as we did as moment of inertia of the rod plus moment of inertia of the particle. Okay. This whole question, this whole substitution resulted in 5 by 24 ml square. So this will become V0 is equal to 3 by 2 Vy. Okay, this is the same equation we had got over there. 5 by 24 omega L. Okay. But omega actually we will get as a negative quantity later. So this will become plus. Okay, so we are assuming here that omega is clockwise, whereas these two are anti-clockwise. So this is our third equation. So now these three equations have to be solved with the three variables. Okay. So I will just minimize this a little so you can go through it, and I'll verify the answers that you are getting. Okay, so let me just copy paste these equations. Oh, sorry. Let's take this. Let's take this as our equation 1. And we have this as our equation 2, which will give us omega L is equal to minus 4 by 3 2 root 2 Vx plus V1. So we should take this as our second equation here. Okay. And then we have this equation. Okay, so what we can do here is we can substitute Vx in terms of Vy here. So we will get omega L as minus 4 by 3 2 root 2 Vx. Now Vx is how much? It is 2 root 2 Vy minus root 2 V naught. Okay, plus Vy. So omega L is becoming minus of 4 by 3 into 8 Vy plus 1 9. Okay, so this should become 9 Vy minus 4 V naught. That's all right. Moving, I'll come back to that. Second equation, what we're doing. Okay, I'll come back to that. So now we substitute this here. Okay, so we substituted this from the first equation into the second equation. Okay, so we got this. Now we'll substitute this in the third equation. So we get V naught is equal to 3 by 2 Vy minus 5 by 24 into this thing minus 4 by 3 9 Vy minus, is it plus, oh, minus 4 V naught. Okay, so let's see what this gives us. V naught is equal to, this will be 3 by 2 plus this will become 6 into, just a minute, 5 by 24 into 12 by 3, what? Into 12. Okay, so 5 by 2. Okay, Vy plus 5 by 6 V1. You can just check my solving once. So 4 Vy plus 5 by 6 V0. So you're getting Vy is a negative quantity. It's very unlikely. Oh, not negative, it's positive only. So Vy will come out to be how much? Vy is 1 minus 5 by 6, so 1 by 6, so V0 by 24. So Ganesh, you're getting a different value than me now. Okay, you just have to go through these calculations. So once we get that, next thing what we have to do, Vx, we'll have to find, let's say. So Vx will become root 2 into 2 Vy, so that is V0 by 24 minus V0. Wait, but I have to just check this equation once more. This is okay. Yeah, Bhumik, let's come back to the second equation. So in the second equation, what we've done is we have applied this condition that the approach velocity of the point A towards P should be 0. We applied this condition that approach velocity of A towards P, this should be 0. Okay, so Bhumik understood this now? I'm coming to, okay. So Bhumik, you are clear with the second equation now, how you got? Approach velocity को 0 किया ना? Okay, good. So actually क्या हो रहा है? This is showing me that omega is negative ना? So if omega is negative, that means omega ऐसा है. Okay, so my Vy is like this, Vx is like this, and my L by 3 omega, I mean 3L by 4 omega, that term is like this. So that's how the net component of A's velocity towards this point P will become 0, because Vx का ये component plus Vy का ये component R omega के इस component को cancel कर देगा, that kind of thing basically. So that's why here omega is coming out to be a negative quantity, which means that omega is coming out to be this. Okay. So I hope this equation is okay now. Vx sin theta plus Vy cos theta should be the opposite sense of omega into 3 by 4L into cos theta. Okay, this seems okay. So let's substitute the values here. So 4 by 3 Vx tan theta plus Vy. Okay. Tan theta was 2 root 2, so this is okay. So now it comes down to solving the equations. So I have used this equation, which is this one, or this one, whatever. Okay. and I've used these two other equations. So the last one is conservation of angular momentum about the point A. Okay, so mv naught L is equal to 2m into Vy. Vx is passing through this point A, so it doesn't create any angular momentum. And again, I have taken omega initially like this, so minus. Yeah, Somadip, tell me which step. Moment of inertia तो ठीक है ना? 1/12 plus 1/16 plus 1/16, so 8 आ जाएगा. So 24 2 plus 3, 5/24. This is correct. So there is a calculation mistake. I'll just check. Okay. So okay. So let me just check this out. So minus 4/3 into 2 root 2 into 2 root 2 Vy minus root 2 V naught plus Vy. So this is okay. So this will become minus 4/3 into 8 plus 1 9. So this is okay. Minus 4. So that's okay. So then we will substitute this here. So we have V naught is equal to 3/2 Vy minus 5/24 into, so I'll make this plus just, okay. So this will become ठीक तो है. So this is 5/2. This also appears okay. Oh, minus है. Okay, that is where the mistake is happening. This is where the mistake is happening. This is a minus sign. Yeah, I was telling you there's some kind of a mistake. So this term should be, oh, 5/, correct, 5/24 into 4/3 into 4, and that too with a minus sign. Okay, got it. So this will become 10/3, right? Sorry, 10/9. Oh my god, let's just go through this once more. So this here is wrong. So ये टर्म कितना आ जाएगा अपने पास? प्लस आएगा फर्स्ट ऑफ ऑल. अल्टीमेटली माइनस आ जाएगा. 5/24 into 4/3 into 4. So that's 5 into 16/24 into 3. So yeah, 10/9. Is it correct now? Finally, have I got this correct? Okay, good. So Ganesh, maybe your calculation was correct after all. So this is 8/2, so 4 Vy, okay, minus 10/9 V naught. So my Vy will come out to be 19/40. Is this the value you had got? Yes, very good. So good, you got that correct. It's a good sign always. Okay. Okay, so anyway, this is what I'm getting for Vy. So then finally I'll get Vx and all that from here. So Vx will come out to be 2 root 2 into 19 by 40 minus root 2 into V naught. Okay. Or root 2 into 2 V naught. So 36. Okay. My mistake. It is 36. Okay. So Vx is now coming out to be how much? Let's calculate. I'll tell you why we'll need Vx also later. So Vx will come out to be root 2 into 19 by 18 हो जाएगा. Okay. So 1 by 18. So root 2 by 18. Okay. And omega, we will see, will actually become a anti-clockwise omega of that whole term. Okay. So 4 by 3 into 2 root 2 into root 2 V naught by 18 plus 19 by 36 V naught. So 4 by 3 into um, 2 by 9 plus 19 by 36 V naught. That is my omega L. 7 by 36. Oh, so interestingly, this is coming V naught by L. So omega is coming V naught by L only, is it? Okay, very good. Okay. Now we come to the really tricky part of calculating the tension. Just at the moment after the collision has occurred. So Samik, you have followed up to here, right? You got the same things for the V and omega. Okay, very good. Okay. Now see what is happening. The collision is over. Now we are assuming the collision is over and the motion is continuing immediately after that. Okay. So tension immediately after that is acting at this angle only. Okay. Towards this point, at the point A, tension is acting at that same angle of theta. Okay. So now we can be sure about one thing, that the center of mass's acceleration will be like this. It will have Ay and Ax such that this will be the same theta. Okay. So basically 2m Ay is equal to T sine theta and 2m Ax is equal to T cos theta. So we'll have this relation that Ay by Ax sorry, it's inverse, cos and sine. This is the angle with the vertical. This is the force picture just after impact. This is the force picture. So this is the center of mass, and it will have an angular acceleration alpha like this because of the torque. Okay, so we'll have Ay by Ax is equal to, or rather Ax by Ay is equal to tan theta. Which we've already seen as 2 root as the first thing. Okay. Then we'll also have that T sine theta, sorry, T cos theta into the momentum about the center of mass. So that is 3L by 4 is equal to ICM alpha. Okay. So this will become TL by 4 is equal to 5 by 24 ml square alpha. So T will be 5 by 6 m into L alpha. So since we want to find out T, if we can somehow find the value of alpha here, then our job is done. Okay. Now the important thing, the constraints. Okay. So once again, the point A is in circular motion about P. Okay. And it is in circular motion in such a way that it has a centripetal acceleration and it has a tangential acceleration. It has a centripetal acceleration which will be equal to m into the instantaneous velocity of that point square divided by d. So I'll take you back to that earlier picture to understand how much that VA is. VA will be along this line. Okay, so we'll get this value. Okay. And the tangential acceleration of that point A will be the centripetal acceleration. So it's just VA squared. And the tangential acceleration will be equal to d into some d2 theta by dt square, like this. Okay, so now let us go back to the kinematics and understand how much that VA is going to be for us. Okay, so for a moment, I'm just going back to the earlier diagram. Just follow what I'm doing here. So we have seen that we've already made the approach velocity 0. We have applied that constraint. Where was it? This point over here. We made the approach velocity 0. But this also now means that what is the net velocity of the point A? Okay. So from this you'll understand that the net velocity of the point A is going to be like this. It is the vector sum of Vy, Vx and 3 by 4 omega L, which now that we have got the correct direction of omega, we know is like this. So उसका जो actual velocity वो इस direction में. So the point is actual velocity will be something like this. Okay. So the point is actual velocity will be like this. It will be Vx cos theta plus 3 by 4 omega L sin theta minus Vy sin theta. So now from this, you can see that also I can write the acceleration of the point A as the acceleration of the point A with respect to the center of mass plus acceleration of the center of mass. So when you're looking in the center of masses frame, so the point A has an acceleration like this. Okay. Like this. Okay. So this is the net acceleration. Okay, you can see that this is basically this term acceleration of A with respect to center of mass is equal to 3 omega square L by 4 I cap minus 3L by 4 alpha J cap. Okay. And this term, the acceleration of the center of mass itself is minus AX I cap, or you can just write it. So this is the acceleration of the point A. Okay. So this point's acceleration, its component along this direction, the centripetal direction, should be equal to how much? It should be VA square by L, where VA is this much. Its component along this centripetal direction should be that much. So it's a bit of a lengthy equation, but okay. So when we incorporate this thing over here now, we can see that the net acceleration towards the center, that will be AX sine theta plus AY cos theta, okay, minus 3 omega square L by 4 sine theta minus 3L by 4 alpha cos theta. This should be that centripetal component of A's acceleration. So this should be equal to VA square by D. Okay. Now I'll tell you what is the easiest way to do this. Okay. Since we want to find tension, so we will write all these terms in terms of tension. AX can be written in terms of tension. AX is equal to T sine theta divided by 2m. Okay, and EY is equal to the vertical component T, I mean not vertical, but the Y component T sine T cos theta divided by 2m. Okay, and alpha also can be written in terms of T. So we can see that L alpha from this equation, equation number 2 earlier, L alpha is equal to 6 by 5 T by M. Okay, so all these three terms, AX, AY, and alpha term is being written in terms of T. See, and omega square we know. I mean, omega we already know from before. VA we already know because from this equation we'll find the value of VA. Okay, so then from that we can find the value of T. So actually, I think one of the equations we've written above will not even be required here. We just check. This equation will actually not be required. We are actually going to just use this equation and this equation because we want to find T now. We don't really want to find AX, AY. So we'll just use this in reverse order, that AX can be written as T sine theta by 2m and AY can be written as T cos theta by 2m. Okay. And we have to substitute those things all over here. So Samik, this is clear, beta? Good. Okay. Yeah, I saw your message. Good. So let's just plug in all these values. So Vx, omega L, ये सब आ गया था अपने पास ना in terms of, so we had these values: root 2 by 18, 9 by 36, and V naught by L. Okay. So root 2 by 18 into 1 by 3 plus 3 by 4 V naught into sine theta, which will become uh, 2 root 2 by 3. Okay, minus this was how much now? 19 by 36 into 2 root 2 by 3 V naught, is it? Yeah. So this is what I am getting. You can just check once. Okay. So now this equation becomes like this, that uh, t by 2m sine square theta. So that will become 8 by 9. Okay. Plus t by 2m into cos theta, which was 1 by 3 into, so cos square theta, so 1 by 9. Achha, so anyway, this has to become, actually, you can do it that way also. There is a shortcut trick also that we could have used here, because this term will actually become a into sine square theta plus cos square theta. So it had to be a only, which is t by 2m. But anyway, we have done it this way, the hard way. Okay, minus 3 by 4 v naught square by L sine theta. Okay, plus, or rather minus 3 by 4 into L alpha, which is 6 by 5 t by m into cos theta, which is 1 by 3. So this should be equal to VA square, which is V naught square by 18 divided by D. So finally, after all this effort, we should get the value of T from this. So you 1 by 2 minus 3 is cancelling out. So this will give us 3 by 10 is equal to V naught square by 18D plus root 2 by 2 V naught square by L. So 0.5 minus 0.3 will give you 0.2. So 1 by 5, so 5m by this is what I'm getting 40. Five by 4 instead of 5, is it? Maybe some mistake I've made. Yeah, I'll just have to double check the calculation here. But the method has to be this only, and it's quite a tricky problem in terms of this. Okay. So Samik, in all probability, there's some calculation here that we have to double check. But up to this step, it must be correct. Okay, now Ganesh, you were talking about that question to do with the double slit experiment only, no? The one you have sent me. Yes, so I'll explain what I have understood in that question. So what is happening is, see, if you have this situation, you have, this is where the single slit is. So that's like the source slit, what we call. And these are the two slits, S1 and S2. Okay. So now, okay, if this distance is some r, and this distance is some r, and this distance is some x, and this is of course a fixed distance d by 2. This is a fixed distance d by 2. So this source is radiating a fixed amount of intensity. So let's say that intensity is I naught. So then the intensity which is, or let's say it's, forget about intensity. Let's say this is emitting a fixed amount of power. Okay. So now things will get a little bit tricky because this power depends on where the monochromatic primary source is. But let's assume the monochromatic primary source is very close to this. So this power is more or less a fixed quantity. तो यहाँ पे जो इसका इंटेंसिटी होगा ना, S1 का जो इंटेंसिटी होगा I1, that will be P upon 4 pi r square, okay, multiplied by a factor which will be like this area, or you can say the power of light projected by S1 will be the intensity of light which is incident multiplied by a projected area. So if this slit has a thickness like, let's say, W over here, then the projected area will be like the projection of this W along this line. Getting my point? So if the thickness of that slit is W like this now, and light is coming in this direction, okay, from S. So we will have to take the projected thing here. You understanding? The projected width W prime, let's say. So that will depend on this factor theta. Okay. So it will be W cos theta into whatever length of the slit is. Because it's a horizontal slit like this. No? Or you're seeing this from above, so it's a vertical slit like this. Is this concept clear, Ganesh? So this theta is the angle made with this wall with respect to this perpendicular. So that will be the same as this theta. Oh yes, the wave is cylindrical. That's correct. So we have to take. So let's take this as yes, that's correct. So this power, this intensity will be like this thing. If the length of the the vertical lengths of the slits are L, so this will be 2 pi r L. So that L and L cancels. Okay. So the power emitted by these two slits, P1 will be equal to P2 will be like this. So it will be upon 2 pi into this thing, cos theta divided by r. Now cos theta here is how much? It is d by 2. So this will be d by 2 r square. Okay. So basically the power emitted by slit 1, that is the intensity incident multiplied with the projected area. That kind of concept we are using here. Okay. So the intensity incident is the power of the source slit divided by 2 pi RL, and the projected area is W prime into L. So that becomes W cos theta into L. Okay. So sorry, cos theta is not d by, it's x by. This is where I made the mistake. So is that kind of non monotonic type of function. So this P1 is equal to P2 will be Px upon 2 pi into d square by 4 plus x square. This kind of term. So now you can see the behavior of this function is non-monotonic. The behavior of this function y is equal to x upon x square plus d square by 4. No? So y is maximum when x is equal to d by 2. Okay, nice. That sort of function. As a function, right? So initially, let's say x is very large. So as x decreases, it will increase, which is what I told you that day. But then as you bring it closer, now there is also the nature of this function which affects it. So the power of light emitted by the individual slits S1 and S2 first increases, crosses the maximum point when x is equal to d by 2, and then decreases. Is this clear, Ganesh? You can also make it a function of theta. You can also make it a function of theta. And yes, this has to be correctly written as 2 pi RL. If I had written it as 4 pi r cube, pi r square, I would have got the wrong result. I would have got analytically the same thing because it would be similarly a non-monotonic function, but I would have got the wrong maxima point. So we can also do one thing. We can write r and x in terms of theta and small d, which is constant. So we can see as theta is changing, how that non-monotonic function is changing. From that also we can analyze. Okay, good. So people, we will conclude today's lecture here today. Originally, I had planned to Bhaumik, your question. Just a moment. Yeah. I forgot. Wait. That question I think we should be able to discuss. Just give me a moment. And Devesh, there's one question of yours also pending. I will send you some hint and we will discuss that question in the next lecture also. Moving, see, in this question now we have to just use the formula for this thing. The okay, let me put up the question for everybody first. Just a second. Trying to share the question, just a moment. Yeah, so when light of this wavelength falls, when light of 540 nanometers falls through the slit, you are getting a diffraction pattern, single slit diffraction pattern like this. Okay. And whereas when light of some unknown lambda falls, okay, so what you can see, the connection between the two is where you're getting the first maxima for 540. That is where you're getting the first minima for the unknown lambda. Okay. So what is the position of the minima or maxima in a single slit diffraction? This is your screen and this is your slit. So at an angular position theta, which you can also take as y by d, theta which is approximately equal to y by d is equal to, so basically sine theta is equal to lambda by n, sorry, n lambda by d, no? N lambda by the width of the slit, which we generally take as A. This is for minimum. Okay, so this is approximately sine theta only. So n lambda by A. This is for minimum. Okay, so if this is some unknown lambda which we want to find out, then this distance, whatever it is, y1, let's say, y1 by d is equal to 1 into lambda 1 or lambda prime, whatever, divided by E. You understanding, Bhumik, this equation? Okay. Whereas this one is where the first maxima is. Okay. So for this one, for the first one where lambda is equal to 540 nanometers, for this one what is happening is that your phase difference there should be, I mean, you should be getting a maxima. So the net intensity is the central maxima's intensity into sine square beta upon beta square, no? This kind of equation where beta is what was it now? Beta was equal to A by lambda into I mean 2 pi by lambda into A sine theta, that kind of thing. Pi by lambda into A sine theta, sorry. Yeah, it was pi by lambda into A sine theta. So you can say it is approximately pi by lambda into A y by d. Okay. So इसका जो first maxima point होता है ना, that's a very complicated thing. The central maxima is for beta equal to 0. So that is y equal to 0. But first maxima is at what kind of a point? So for that you have to actually use maxima minima concept. Y is equal to sine square theta divided by theta square ka maximum, other than when theta is tending to 0. So it's a bit of a complicated value. I don't remember it, but you have to use differential calculus to find out the maxima. So one of the easy ways to do it, because it's for a small theta only comparatively, so you can open up this equation by power series also. Power series might not help. You can try that, because it's for comparatively a small value of theta. So what you can do is you can write sine square theta in terms of cos 2 theta. So sine square theta will become 1 plus cos 2 theta by 2. So this will become like this. Okay. And then you can open this up by power series. Maclaurin series of cos 2 theta. You can open it up by that. And then differentiate that and put it equal to 0 and see where you are getting the first maximum. Okay, I'll just try to get you the value of the first maximum. Just hang on a second. So if I remember, that comes from quite a complicated analysis of sine hyperbolic square function. Okay. So this type of question is not actually going to be asked. Okay. But anyway. Okay, at a glance, I'm not able to recall the value, but there is some value of theta, or in this case, this beta, for which you will get the maxima. There's some particular value of beta. So when you put this thing, pi by lambda a y by d equal to that value of beta, which you're getting over here for the maxima, you will be able to understand the relationship between this lambda, where this lambda is now going to be 540 nanometers. So you'll be able to compare this equation with this equation earlier that we had seen. The first one's minimum, this equation that we had seen. So you'll be able to compare these two equations. Okay, because this will be the same y1, but this is giving you the condition for maxima, and this is giving you the condition for the first minima. So you'll be able to get the ratio of the lambda and lambda prime. Is it clear, Bhumi? Okay, so I'll send you the exact value of the beta at which this happens. Once I find it, send it to you. Okay, so we'll conclude here today, people. We'll continue next week with some more doubts, and also with the revision of fluids and properties of matter, which I planned to start today, but we couldn't do. We'll start it in the next week. Okay, Aditya, I'll send you some doubts from some hints for your doubt too. Okay, so that's it for today, people. Wish you all the best.